given by Jennifer Haase, talking about atmospheric rivers.
Hello. Okay, my talk today is about atmospheric rivers in 3 dimensions. The work I do on atmospheric rivers is in collaboration with the Center for Western Weather and Water Extremes, so I acknowledge them here on the first slide, and the ARO team. And this is my ARO team here. They're all here in force, each with a poster ranging from spaceborne RO to the system description and data assimilation. There are many new early career scientists, so I encourage you to stop by their posters. And I also want to extend a special thanks to Cosmic Program for their student travel program. I want to announce I have 2 positions open, one postdoctoral research position with quite a bit of flexibility on what the topic may be, and then a GNSS research analyst position. Just email me or one of the team here about that. I wanted to advertise our data sets and a new paper that Bing Chao has put out that just gives a complete system description. Anything you want to know about airborne radio occultation, you can find it in this paper. And one of the things I really like you to know is that we always give you the very best data that we have. We always give you all of the data that we have. We always try our best to pursue and continue our development and provision of data in a very consistent, systematic way. We're now 5 years of AR recon measurements with our 5-year plan, have now moved our measurements onto 5 aircraft, and we plan to continue that. So you can rely on this information coming in. And also, we are in a research and operations partnership. We provide the same quality data to anyone working in the operational community and in the research community. And it is a partnership where we work together to move forward on data assimilation. And I make the observation operator available here at this website. And you can talk to Powell. He's here presenting a poster as well. This is a map of the total precipitable water vapor. And you can see an atmospheric river here, heading towards California on the 4th of January, 2023. Long filament of water vapor that's here. You can see it wrapping around the parent cyclone as it approaches the coast. And most of the water vapor transport meridionally is through atmospheric rivers. They're really important in California because 84% of all the flood damages comes through atmospheric river storms. And so there's a big difference between a year like 2019, where we get many atmospheric rivers and 200% of the normal precipitation, versus the opposite when we have very few ARs and we're down to 10% of our normal precipitation. And so water security is a huge challenge in the West. And some of the people that work with the center are relying on forecasts for managing water resources. And so this is important to the end users as well. All right, so just the conceptual view of atmospheric rivers and how we design the measurements that we take in the AR recon missions. We're trying to sample essential atmospheric structures associated with the low-level jet in front of a cold front, a low pressure system here, and we look at the potential vorticity in the trough, and also the ascent in the warm conveyor belt associated with uplift in the atmospheric river. These are the features that we're targeting when we fly these campaigns, and we also use information from adjoint model sensitivity calculations to plan these flights. And these are really to work in as a complement to the extensive amount of radiance and satellite data that we have to just help densify the observations in this mid-level cloudy region where it's more difficult to get high quality radiance data. So this is our target region, and the arrow sweet spot, it's everywhere below the aircraft altitude of 12 to 14 kilometers. and down to about 4 kilometers with our existing conventional systems. And then we have 2 students here presenting posters on our work towards making these measurements in the lowest part of the atmosphere. But I'm going to concentrate on these mid-levels here in this talk. So this is a reminiscence back to Cosmic One and one of the first papers on atmospheric rivers and radio occultation with Bill Kuo here, one of the co-authors, taking a transect of Cosmic One profiles across an atmospheric river, recognizing the importance of the moisture for the predictability of these storms and looking at what, when you interpolate the humidity retrieved from the ARO profile, from the RO profile, just doing a simple interpolation to look at how that humidity is associated with the frontal structure in this atmospheric river low-level jet. So we're going to value, there's value in examining in detail this kind of structure of what the radio occultation measurements are sensitive to. And so I'm going to do that with the increased sampling that we have with the airborne radio occultation. So I introduced this concept of refractivity anomaly in the earlier paper, where it's just the refractivity profile derived from your observations minus some climatology that accounts for that more or less exponential increase in refractivity with height, and then appropriate for the latitude that you're at. And this refractivity anomaly I show here, it really highlights the vertical structure in atmospheric rivers, separates the effects in the UTLS that are primarily due to temperature and the variations in the lower troposphere that are primarily due to moisture. And so you can really see, this is Marty Ralph just plopped his cartoon right on top of a figure with no adjustment to scale. And it just shows that we see the stratospheric air descending here behind the cold front. And we also see this warm low-level jet as it's uplifting over the warm front. And I'll show you several examples. My objective today is to kind of give an idea of what these atmospheric rivers look like in refractivity space, because many of us are looking at our observations in refractivity space. This is an example of an AR from last year, 2023 in January, where we are flying out of Hawaii, and we have a more or less straight transect that crosses over 2 atmospheric rivers, one that's more fully developed in the tail end, and then one that's approaching. And so we have dropsondes being collected, 27 dropsondes along part of the transect, and then the full length of the transect, we have 62 multi-GNSS ARO profiles on both sides of the flight track. So what does this look like in a cross section along that flight path? These are transects from ERA 5. This is specific humidity, and this is temperature. You can see the frontal structure here. And this is refractivity gradient from ERA 5. So white lines on here are each of our ARO profiles projected onto the plane of that transect. So with this conventional system that we're using now, we typically get down to 3-4 kilometers altitude. Maybe 20% of the time we get down closer below 2 kilometers. And I understand that this is not good enough for a lot of the things we want to do, but there's a lot of information here. So you can see in the refractivity gradient a really strong structure here. We'll go to this is the transect in terms of refractivity anomaly from the ERA 5. So it really pops out here, the structure of enhanced moisture in the atmospheric river itself, in the core. And then also we can see the subtropical dry air in the warm side and really capping the moist boundary layer here. And of course, we know the boundary layer is not the refractivity gradient, but you can clearly see those structures. We also see the second AR as enhanced moisture back here. We see cold, dry air behind the frontal structure. and we see really enhanced moisture. Every one of these curved lines is one ARO profile. So this that was my reminder here. This is my, this is superimposed our ARO profiles onto the transect of dropsonde profiles. So you can really see we're picking out the same structures. And the thing that I'd like to point out here is that we don't penetrate to the surface, but you can see that our measurements are catching that there is dry air underneath this, this moist atmospheric river, and that it's sloping in this direction. And the existence of this is nothing new. It's Browning et al. 1997 has already described this kind of dry intrusion. But it's new that we can, when we look at it in this way, we can actually see these variations, and we can see the indication that there's dry air in front here. So I'm gonna move forward. I included a couple other examples in the presentation for you to look at, but I'm gonna concentrate on this one where we did data assimilation from this transect here. You can see a similar profile. We have the high pressure subsidence creating a strong dry feature here, the AR core, and then a dry air back behind here. It's kind of hard to see what's going on with, you know, these blue points here. So I've got a, now I need to get this to move. Okay, so I've rotated all of these profiles, and you can see structures. You can see this mid-level moisture rising up in the middle of the, in the middle here. You can see that these blue dry points are on the backside of the atmospheric river. You can really, this structure really comes out here in the refractivity anomaly. So this is interesting because when we do data assimilation and we, for example, have a control experiment without ARO, and we look at the difference with ERA5, in the region where we have observations, control experiment was actually too dry in the mid-levels. And then if we look at after we assimilate the RO, we can look at the change in the RMS error here when we assimilate the ARO. We can compare those two, compare the RMS, and we have a better RMS in most of this mid-level area when we assimilate the ARO. And what's going on here, there is this structure, this moist mid-level moisture in this structure that we saw in the representation, and that's the feature that we're actually improving. So this was a case where there was actually a 3-day forecast mismatch between the EC and the GFS, a big shift in where the AR should have been, where the core of the AR should have been impacting the coast. So this is what we're trying to improve. And with these preliminary results, NE has a poster 5B, we have improved, this is the region of improvement of precipitation in some of the terrain-related orographic precipitation. So in conclusion, we can get a higher resolution picture of the AR structure when we look at it in terms of the refractivity anomaly, especially with the density of profiles that we have in the storm region with ARO. They constrain this sloping nature of the AR core and this dry post-frontal air underneath. We get a good location of the mid-level moisture as it ascends in the warm conveyor belt. And we can see clearly that there's this disruption in the marine boundary layer due to this upward mixing of moisture at the AR core. And that actually sometimes allows us to penetrate down into the AR core. We see the descent of this dry stratospheric air from the tropopause in the frontal zone. And we can usually, we always see the effects of the subtropical high and high pressure in generating a strong DNDZ gradient, and we can see that drop in moisture at the bottom of many of our profiles. So I just think it's interesting to provide some view of what the system is that we're actually trying to improve. And then when we look at it in terms of data assimilation, we can understand which aspects we're actually improving. So thank you very much.
Thank you very much for your presentation. I think we have time for maybe one question. Okay.
I've got one quick one. In the AR Recon that's going to be upcoming this fall, is there potential to have that data distributed by NOAA? I know you'd mentioned you were working on that.
We're working on that. Bing Chow is our main person. He's been working on. We know we can deliver it if he's sitting there at the computer. So we're just trying to improve that. Some of the mechanics of the actual transmission of buffer data, but we plan to be doing that this year. Season probably starts in. We're not sure when the Air Force is going to start flying there. Actually not, they don't have the capability to transmit, but NOAA starts January 7th or something.
Okay, thank you very much. We are going now to switch the chairs. Please come up. And maybe a quick information. We changed now the timer to 13 minutes. That's the time for the presentation. And you have 2 more minutes for the discussion.